Swayam Prabha. Digital India. Educated India.
Okay, good morning. We will begin our lecture today. The topic we are going to cover is the mechanical properties of high-entropy alloys. And before I move on to the next slide, I just want to make sure that when we talk about mechanical properties, we should have some idea about the basic deformation mechanisms, like how the plastic deformation occurs in solids, right? So, in fact, some of the slides we have shown in the characterization, I have showed the deformed structures, right? Like how the deformation structures look like, how the slip bands look like, how the twins look like, and also I showed some of the dislocation structures in a TEM, how the dislocation lines will look at and all that. So, what we have to remember in this topic is, so look at some of the basics. Like, let us recall some of the basics like dislocations. You understand what is dislocation core, right? So when you say dislocation core, then it has got some energy, right? So when we talk about the lattice without defects, lattice with defects. So the energy we talk about is the difference in this energy between a vacancy or a dislocation, any defect, and the lattice. The difference in the energy, we talk about the energy of that particular defect, right? Or in this case, in high-entropy alloys, if you look at the lattice, we say the lattice is distorted, right? When you say distorted, then you have to relate that with the normal lattice. So the difference between a pure defect, the energy difference between any defect and a pure lattice will be smaller in the distorted lattice, because the lattice is already distorted, it has got some excess energy. So that energy will be smaller. So that means when I want to annihilate a dislocation, the energy requirement in the distorted lattice will be smaller than the pure lattice. On the other hand, if you look at the any of these mechanisms, because you have already a distorted lattice which has got an additional energy compared to a normal lattice. So the dislocation, the core energy is also slightly different from the conventional pure metal or any alloy, because it is completely a multi-principal component alloy which is completely distorted. So when you talk about a dislocation core, you have two kind of stress fields. Like you have, if you consider a classical edge dislocations, the upper side is experiencing compression, and the lower side is tension. So you have all the substitutional elements can go and occupy the tension region, so that it will reduce that stress, it try to relax that stress. And similarly, any small atoms can go and occupy the compression stress field, so that will try to relax that. So this kind of idea we should know. And then also we know that popularly known as stacking fault, right? So when you look at the broad classification of materials, like you have the materials which during deformation they exhibit a wavy slip or a planar slip. Okay, so these classification stems upon the concept of the stacking fault energy. The material will exhibit very high stacking fault energy. The dislocation movement will be easily permissible, or the dislocation, three-dimensional motion of the dislocation structure is easily possible. That means we talk about the cross slip, multiple cross slip, and so on, which is easily facilitated. But when you have the stacking fault energy which is low in a material, then your defect structure will try to rearrange only in a planar fashion. So you will have the planar array, where we can also see that instead of looking at a cell structure which requires a kind of a three-dimensional mobility of dislocations in any of the deformation or during plastic deformation, in a planar slip you try to form a network of dislocation, possibly a hexagonal network or a line of slip bands. So that means the three-dimensional mobility is restricted. So in the light of this high entropy alloys, most of the high entropy alloys, when you add additional multiple principal alloying element, the stacking fault energy comes down. So even if you go to any literature, vast literature is there, if you look at all the as-cast microstructures, you can see already the boundaries are already filled with quite a bit of a dislocations array, and you can see some of the cases, you can see the hexagonal network is in the interface and so on. So this clearly tells us that the dislocations are existing in the as-cast condition. That means they can be manipulated. It brings down. The stacking fault energy generally comes down. This is what the literature says. But of course, there are exceptions. But mostly the stacking fault energy comes down. So in the interest of time, I did not get into all the fundamentals, but I just want to give a prelude for before we look at even a indentation that is involving a plastic deformation. So we have to keep all these parameters in mind, right? So because a plastic deformation is mediated by a slip, then when you say slip, then dislocations are moving in a particular plane, right? So this is a kind of an idea. So with this idea, we will we will start our discussions. When you come to mechanical behavior, the first property one would look at is a hardness, because it's very easy to do in a laboratory without any sophistication. And if you look at this table, it's quite, this plot is highly populated plot, and you can see that 20 high entropy alloy systems are compared with the conventional alloys, and then you have an alloying system here is plotted in the Y, and the hardness values are higher. So you can see that most of the high entropy alloys exhibit much higher hardness than the conventional alloys. So we know the reason, right, why the high entropy alloys exhibit high hardness, because primarily the solid solution strengthening effect, and then of course all type of strengthening effect also play a role in high entropy alloy, like you have solid solution strengthening, grain boundary strengthening, that is grain size, and then precipitation hardening and work hardening and so on. All these conventional mechanisms still operate, but nevertheless the high entropy effect is also, the solid solution strengthening is also one of the primary strengthening mechanisms in this. So we will look at this hardness values, and then what are the contributions for this class of materials, right? So what we have now looked at is about 20 most studied high entropy alloys. So these are all from the literature. Everything is taken from this book, whatever I am presenting. It's a very nice book for introduction, and they are compared with the conventional alloys in the figure. For example, we have looked at this particular aluminum, cobalt, chromium, copper, iron, nickel alloy system. We looked at in most of the studies, even in the characterization we looked at it. So this kind of alloy has been widely studied. The hardness values vary from 154 to 658 HV, and they are strongly dependent on the exact chemical composition, fabrication methods, heat treatment processes used. Obviously, we all know that what kind of different fabrication methods are being used for producing high entropy alloys, and every processing method will have its own influence on producing a particular microstructure. Of course, it can be heat treatable to any required hardness. For example, the hardness values of other systems like aluminum, chromium, iron, manganese, nickel, or aluminum, chromium, iron, moly, nickel are generally higher than the conventional ferrous and non-ferrous alloys. That's what we have seen in the figure. However, the hardness values of the as-cast high entropy alloys, mainly with the face-centered cubic phase. For example, if you take cobalt, chromium, iron, nickel, or cobalt, chromium, copper, iron, nickel, or cobalt, chromium, iron, manganese, nickel are generally low at room temperature. Still, those containing appreciable amounts of aluminum and titanium are generally high due to formation of stronger secondary phases. So, this is very important. Though we say that FCC high entropy alloys generally exhibit a low hardness at room temperature, with the addition of aluminum and titanium, because they form a stronger secondary phases, the hardness value will be higher. And another important class of refractory high entropy alloys, which we will also talk tomorrow on the high temperature properties, it is a new class of high entropy alloys, and which are mainly body centered cubic phase, relatively high. The hardness of this phase is relatively high. You can compare the values. It is 390 HV, 454 and 535 and so on for the BCC, high entropy alloy like hafnium, niobium, tantalum, titanium, zirconium, titanium, like moly, niobium, tantalum, tungsten, and then moly, niobium, tantalum, vanadium, tungsten, and of course you can have the variation of this niobium and titanium added in this alloys, which also alters the hardness very effectively. So, what we are learning from this kind of data is that a selection of alloy system, adjusting the composition ratio within the alloy system, and the choice of alloy processing methods are critical in determining the alloy hardness of high entropy alloys. This is well known. I mean, there is nothing new in this, but in the case of designing the high entropy alloy, one need to be very careful about this. Well, people use all type of methods. In fact, Gerhard will present different type of processing these methods. You can do casting, you can do powder metallurgy route. There are different methods possible. All conventional methods people use. So, depending upon the volume you require, depending upon the applications, for example, some alloys are easy to melt, some alloys will not be easy to melt because of the high melting point and so on, miscibility. See, again, you have to decide. I think the first class I just talked about the phase selection rule. So, you want to form an FCC solid solution, or you want to form a BCC solid solution, or you want to have a mixture of them. So, all these things have a role to play, which processing method you should use. And then some of the methods will be energy intensive, some of the methods will be energy friendly, and then some of them may be possible to produce in small buttons. You can do all type of sophisticated new techniques you can adopt, but then if you need it in a bulk, if you want to scale up, then that is going to be a huge challenge. So, all these factors will come into play. Of course, for an academic interest, you can do any kind of a new alloy you can produce, but that can be done only in a small quantity, or you can take different powders and then mix it and then compact it and then produce this. So, how does this hardness is going to be manipulated? First is annealing effect. Suppose if you anneal this alloys, all these alloys. So, what we have seen in these two plots is you have the hardness values and then hardness ratio, that is hardness divided by the original hardness. That is, before annealing you have a hardness, after annealing something else happens. So, you have a hardness ratio, and then you have a two type of colors are shown here based on the effect of annealing treatment on the hardness. High entropy alloys are divided into two groups: strong edge hardening, red lines, and weak edge hardening, black lines. So, you have so edge hardening is something like you have a secondary phase formation, that is a very classical phenomenon in metallurgy. So, in this case you can see that as a function of annealing temperature, then it is kind of a peak aging. You know that, which is popular in aluminum alloys. Similarly you are seeing a peak hardness at a particular temperature and then it comes down. So, this is related to the second phase formation and its coarsening and so on with respect to hardness. And some of them are weak edge hardening. That means they do not respond to annealing effect. That means they don't form any significant secondary phases which will contribute to this precipitation hardening effect. Okay. So, this is one classification where you can look at the basic property of high entropy alloy just by measuring the hardness and what is the annealing effect. Yeah. And then let us look at the temperature dependence. Like, so the strong high temperature edge hardening happens in several alloy systems. For example, if you vary the aluminum content, we have seen the several alloys in the previous classes. You can aluminum high entropy alloys are quite popular because several people have studied. So, if you vary this content, aluminum content from 0.3 to 0.5 in this aluminum, chromium, iron 1.5, manganese, nickel 0.5. So, all these are FCC structured high entropy alloys, these three high entropy alloys. They have shown a very strong high temperature edge hardening. This type of very strong high temperature edge hardening phenomenon is seldom found in conventional alloys. This is something interesting in high entropy alloy and which is an advantageous. Okay. High temperature edge hardening is not a usual phenomenon in a conventional edge hardening behavior. And if you look at why this high temperature edge hardening behavior is happening, this is attributed to the formation of precipitates. What kind of precipitates? You have a row phase. Row phase is Cr5, Fe6, Mn8 phase in this aluminum, chromium, iron, manganese, nickel high entropy alloy. And then you have a nickel aluminum rich B2 phase. If you change the aluminum, cobalt, chromium, iron alloy. Okay. The dual precipitates of nickel rich phase and a chromium, molybdenum, cobalt, iron, nickel sigma phase in aluminum, cobalt, chromium, iron, nickel, moly alloy, and a nickel, chromium, titanium rich B2 phase in this particular alloy. So, what you see is at high temperature you have new phases forming like a row phase or a B2 phase or a sigma phase. So, you can understand like that. These are all very strong high temperature phase. I mean, it forms at a very high temperature and then they contribute significantly to the hardness. These are all basically intermetallic, very strong intermetallics. It forms at very high temperature. However, when the temperature is above 900 Kelvin, the hardness of these alloys decreases because of the thermal softening. That is well known. How about alloying effects in the is recognized for the hardness? Okay. See, the hardness is very widely studied in this alloy because this is a basic property. And when this field started growing and everybody started making all sort of combination of chemistry, the first information you can get about the mechanical behavior is hardness. So, it has been studied thoroughly. Okay. So, here people have looked at the Vickers hardness of aluminum, cobalt, chromium, copper, iron, nickel, of course with the various fraction of aluminum and cobalt and so on. And with different aluminum content, then you can see that the hardness is significantly increased. So, the aluminum contribution to the hardness increase of multi-phase high entropy alloys was related to solution hardening mechanism, precipitation strengthening effect and the nano composite strengthening effect. So, you have three different contributions. It is not just precipitation alone here. So, when you have a particular chemistry, for example, the previous slide we talked about edge hardening, that means you have one particular phase forming, and then we talked about high temperature edge hardening, that means you have a specific intermetallic forms only at high temperature. But you can also tweak the alloying element such a way that you can get this precipitation strengthening as well as the nano composite strengthening effect, composite strengthening effect. Several mechanisms can be combined to exploit this strength of the material. And another example for this alloying effect is like you can just vary boron nickel vanadium ratio again. You can also vary this cobalt chromium niobium molybdenum ratio. This all can show a different kind of effect. You can see that various type of alloying will give a different trends of hardness increase and a decrease and so on. So this is quite interesting. And very important thing is hot hardness. What is hot hardness? We talked about hardness, which is normally we do it at room temperature. Hot hardness as a function of temperature, that means you can do it at a very high temperature, right? You can in situ kind of a measurement you can do. For this aluminum, cobalt, chromium, iron, nickel base, similar kind of high entropy alloys, they show the very high hardness, high hot hardness, and have a potential in high temperature applications. So what you are seeing here is different kind of alloy. This is aluminum, cobalt, chromium, iron, nickel. This is aluminum, cobalt, iron, moly, nickel. And here it is aluminum, cobalt, chromium, moly, nickel with a different molybdenum content. So you can see that as a function of temperature, how the hardness is decreasing. If you look at the hardness change, it is not drastic because the temperature increase. It is a gradual change. It is not a very drastic change. Okay. So if you look at the numbers also, it is quite impressive. You have 660. You start from 740 to 340 HV, ranging from temperature ranging from 300 Kelvin to 1200 Kelvin. The softening coefficients of pure metals such as molybdenum, nickel, chromium, nickel, silicon and iron are 2 orders of magnitude larger than those of high entropy alloys, indicating that alloying indeed has a tremendous effect on lowering the softening coefficient. So you are looking at as a whole alloy and then individual elements. So you compare this, softening effect coefficients are quite different. It suggests that the sigma phase is the main strengthener at high temperatures, like which we have already seen in the previous slide. And this aluminum, cobalt, chromium, iron, moly, nickel alloys and aluminum, cobalt, chromium, iron, nickel alloys have respective hardness valued at high temperatures shown here. Whatever these two alloys have pretty high hot hardness at different temperatures. Okay, so that is about the hardness. Then the people just looked at immediately hardness. People wanted to study the strength. Usually we do it strength measurements by the tensile test. That's a standard test. But in this particular case, people started doing only compressive properties because the volume of the material synthesized was too small to fabricate a sample. So for compression test can be studied just making a small cylinder and then we can compress it between 2 plate ends and then measure the strength and elongation. Okay. So the typically for all the alloy system whatever we have studied, we will look at the compressive properties in a very detailed manner. And of course, you can also vary the strain rates like 10 per second to 10 to the power minus 3 per second. So I am not sure the, okay, it is clear there. You can look at the typical stress strain diagram and you can also see this, as a function of temperature, how the compression curves are changing from 300 to 1200. It's nicely shown here. This is at high strain rate of 10 per second and this is a normal strain rate like low strain, that 10 to the power minus 3. You can see that how the compression curves are changing. Do you see a difference between these two? Temperatures are same almost. Strength is different, right? This is because the high strain rate effect. So strain rate also influences the strength, right? And what is interesting is all these high entropy alloys behave differently at various temperatures and strain rates. Okay. So, if you look at the metallurgical literature, the material which behave at a high temperature is always correlated with the high strain rate. Okay, these two phenomena are, no, I mean the kind of property you observe in a high strain rate, you will also expect that in a high temperature. It's a kind of an idea. But here if you have a close look at the plastic region, that is this region, this is a completely plastic region. A serration behavior can only be found in specific temperatures and strain rate regions. So, the serrations are not found in all temperatures. I think here it is very well pronounced at low temperatures here, and at high strain rates is very again very small regions we see the serrations. And so, we'll talk about the serrations a little later, and which are at a temperature of 873, 973, 1073 and 1173, and the strain rate of minus 10 to the power minus 3 per second. This trend implies that diverse deformation mechanisms may exist. So, you have different deformation mechanisms at low temperature, high strain rate, low temperature, low strain rate, especially the serrations. Okay. Do you have any idea why serration occurs? No. Okay. So, there could be two reasons. It could be a dynamic strainaging or twinning, secondary phase formation. Okay. But why that is not seen in other temperatures? So, that is another interesting point. And if you look at the fracture surface of this compression tested sample, and then you can see a very interesting idea. So, here it is the effect of copper addition on the compressive fracture surfaces at room temperature is shown. And then what you see is high density of dimples here, and what you can see that a dimple-like structure is related to micro-void coalescence. This I showed yesterday, how the micro-void coalescence or aggregation, which is a typical feature of a ductile fracture. And as the content of copper increases, the dimple-like structures gradually decreases. You can see that the dimples are coming down as you keep on increasing the copper. And what you see is instead tear edges and cleavage steps. So, these are all cleavages and tear edges you can see, and these features begin to appear as denoted in the white arrows here. Okay. So, which is caused by the coordinated operation of dislocations and micro-voids. So, this is one idea about these compressive properties. The combination of both features, that is tear edges and cleavage steps, can be classified as a quasi-cleavage. Quasi-cleavage means it is neither ductile nor brittle, it's in between. And with a further addition of copper, planar facets and river-like patterns can be identified, which is the typical cleavage fracture morphology. Cleavage fracture is usually a characteristic of a brittle behavior. So, the analysis of the fracture morphology agrees very well with the corresponding stress strain curves, which show the plastic strain of 9.05% in aluminum, cobalt, chromium, copper, iron, nickel, titanium alloy, and it is 6.04% for aluminum, cobalt, chromium, copper, iron, nickel, titanium alloy, and it is very high at as 21.6% for aluminum, cobalt, chromium, copper, nickel, titanium alloy. So, besides this room temperature property, we also talk about the refractory high entropy alloys, which are primarily developed for high temperature application. Addition of refractory elements improved the mechanical behavior of these alloys compared to the traditional alloys. The compressive behavior of molybdenum, niobium, tantalum, tungsten at elevated temperature is described in a figure which I am going to show in the next slide. all the curves exhibit significant plasticity. The yield strength decreases as the temperature increases. Microstructural examination indicate that localized shear and cracking dominate the deformation behavior at lower temperatures, while grain boundary sliding, void formation should be responsible for the fracture at high temperatures. So basically, we looked at the compression behavior of a normal alloy, and then this is a refractory alloy, and then how the deformation behavior is looked at. This is what shown here. The slide is quite clumsy, so we will spend enough time to understand this. What we are showing in the figure A is the stress strain curve, and B is the stress strain curve as a function of temperature, of course, and you have a compressive behavior of aluminum, cobalt, chromium, copper, iron, nickel alloy at cryogenic temperatures. So this is very interesting plots. And C is the temperature dependence of compressive yield strength for high entropy alloys and conventional alloys. C, all these new alloys are compared with the conventional alloys like Inconel 718, Heinz 230, they are all super alloys, right. So what you see is this is a compression behavior anyway, which we have already discussed. What is shown here in B is it is tested at the cryogenic temperatures of the aluminum, cobalt, chromium, copper, iron, nickel alloy. So the stress strain curve presents an obvious transition from a serrated flow at low temperatures to a non-serrated flow at high temperatures, which indicates a significant change in deformation mechanism. In addition, the sharp saw-like type serrations could also serve as a proof for microstructural evaluation. So that means when you have this kind of a typical sawtooth kind of stress strain curve, you have to look at the microstructure, then you will find an answer. What kind of, like what he said about, it could be because of twinning, it could be because of dynamic strain aging, and so on. Work hardening is also observed at all listed temperatures. That means you have the dislocation activity is also on at all the temperatures. So in order to get the complete details about this structure property correlation, you need to have a thorough microstructural study to clarify how these things happens. So the message from this study is you have high entropy alloys which you have developed for room temperature and high temperature applications, and even for cryo temperature applications it exhibits promising properties under compression test. So we have also witnessed that the yield strength at various temperatures compared to the conventional alloys. The advantage of high entropy alloys is evident over traditional alloys. For example, this molybdenum, niobium, tantalum alloy have a better yield strength than the Inconel 718 and Heinz 238 conventional alloys at high temperatures. Of course, when the temperature is below 1073 Kelvin, the aluminum, molybdenum, niobium, tantalum, titanium, zirconium alloy and other alloys have a better yield strength than the Inconel and Heinz. They are all the reference material for high temperature. That is why we are talking about Inconel 718 and Heinz 230. They are always a reference material. So this is with respect to a temperature effect we are talking. And what about the strain rate effects? So we looked at temperature effect as a high temperature property. What about strain rate effect? The strain rate effect on the compressive stress strain curve of refractory high entropy alloy, hafnium, niobium, tantalum, titanium, zirconium at 1000 Kelvin. And we also talk about later sample size effect. Okay, suppose if I have different sizes in terms of thickness or variation. diameter of the cylinder if I keep on increasing. This is also very important. First we look at the strain rate effect. The loading rate has got a major effect on response time of materials during deformation on their mechanical performance. For example, this hafnium, niobium, tantalum, titanium, zirconium alloy, it is evident that at high strain rates, which is beyond 10 to the power minus 3 per second, deformation strengthening dominates and the plastic flow keeps on increasing in the compression experiment at a temperature of 1073 Kelvin as shown in figure A. So, what you are seeing is this is what we are talking about. So, we are increasing the strain rate from minus 10 to the power minus 5 to 10 to the power minus 2. Okay. In contrast, strain softening occurs after yielding, followed by a steady state for the low strain rates, which is 10 to the power minus 4 per second to 10 to the power minus 5 per second, which indicates an alternative deformation mechanisms. So, you have, if you look at this, there is a kind of a peak and then it softens immediately and then it goes to steady state at these two strain rates. But in this strain rates, it does not show any dip in the yield point, it just continuously increasing at the high strain rate. Okay. So, though these are all the same material, but the strain rate shows a different kind of a stress strain behavior. That means the mode of deformation is significantly changing from the low strain rate to the high strain rate. So, this is called the loading rate or deformation strengthening mechanisms. Okay. What are those? That has to be looked at in the microstructure. No, yeah, 1000 Kelvin, 1000 Kelvin. That is why the refractory high entropy alloys are quite popular, I mean very attractive. Yeah, this is the idea. So, very interesting properties. So, the scanning electron microscopy characterization and extensive wedge-like cavities assembled at grain boundaries with the strain rates of 10 to the power minus 3 and minus 2, which is pretty high, suggesting that pure dislocation, mobility and diffusion activity are not sufficient to accommodate the deformation and relieve the stress concentration around the sliding grain boundaries. Okay. With the high magnification, the fine recrystallized grains and particles can be found along the grain boundaries, indicating the presence of high internal stress and high density dislocations, which may contribute to the formation of high grain boundary cavitation. However, when the strain rate slows down to 10 to the power minus 4 to 10 to the power minus 5, only small round of cavity exists, implying that operation of dislocation and diffusion are sufficient to accommodate the deformation process. So, this is the important thing. When you look at the deformation activity, you look at two things: diffusion, especially high temperature, diffusion and dislocation activity. And how much, because these are all the structural entities which carry the strain or carry the load. So, how densely they are produced, then accordingly the energy absorption will be there. Okay. So, that is the difference what is given here. So, high entropy alloys also show a sample size effect on the compression behavior of the same. For example, figure B I showed a stress strain curve for sample with the diameter 2, 5, 8 and 10 respectively. So, this is the diagram 2, 5, 8, 10 compression behavior. And is it not interesting that you have a thin sample cylinder which exhibit a very high compressive strength and ductility? So, the more the diameter, you will have, see, more defects or more phases or more dendrites. So, those things are not good for strength. Suppose if you smaller this single phase, less defect, that means it will have more strength. It is like a thin wire will be having a very high strength than the thick wire, because you are reducing the defects considerably. That is one rough idea. So, let us see what we have taken from this literature. Smaller high entropy alloy samples exhibit both high strength and larger plasticity. The SEM characterization indicates that the samples of 2 and 5 mm in diameter present similar single phase morphologies, in contrast to the typical cast dendritic structure for larger samples. So, you have a cast dendritic structures will have always a lot of defects and multiphases. EDS analysis implies that the samples of 2 and 5 mm in diameter, the elements within the grains distribute homogeneously. This is another important idea. On the other hand, the two samples with 8 and 10 mm in diameter, chromium segregated to the interdendritic region, and a compound containing nickel and chromium may form during solidification, which could result in a decrease in the yield strength. So, size effect is also very important in the high entropy alloy systems in the compression properties. So, now we are getting into little sophisticated compression test. What you are seeing here is like micro compression testing, which is done under the microscope. This is a focused ion beam microscope, the dual beam, where you fabricate this nano pillars by ion milling, and then you also do a compression test in the microscope itself. So what you are seeing is the SEM images of post compressed 016 oriented molybdenum, niobium, tantalum, tungsten high entropy alloy pillars with the diameters of 2 micron, 1 micron, 500 nanometers and 250 nanometers. And what you see is a corresponding stress strain curve. So, it is quite interesting. The micro compression test has been conducted under the microscope, SEM microscope, and the particular orientation is selected so that you will be able to see the slip, single slip or slip systems. Figures A and B clearly reveals the single slip. So, what you are seeing here is this is a slip, they are showing clearly, and slip bands on the pillars of larger sizes, while multiple slips can be found in C and D. So, here you see multiple slip 1, 2, 3, here 1, 2, 3, here just 1. With smaller size pillars which may contribute the strain hardening. So, the C and D is different from A and B in terms of size, right. So, okay. The stress strain curves in figure E show that the smaller pillars possess larger yield strength, okay, and larger strain bursts with a higher frequency, which may result from more activation and interaction of multiple slips. So, this is another way of looking at this compression properties of high entropy alloys. So, these kind of tests are done when you have very limited access to the material volume, and you can do this kind of idea. And if it is promising results, then you can think of producing it more and so on. That is another advantage. Then we will move to our traditional tensile properties, conventional tensile properties. Unfortunately, the number of studies reported in high entropy alloys for tensile properties are limited because of the volume. People could not produce a huge volume of this material, so they could not conduct that. But some of them have been reported, especially this alloy has been studied thoroughly. In all case studies, we are not missing this alloy: aluminum, cobalt, chromium, iron, manganese, nickel alloy. Again, this you have the aluminum effect on this. So, as the aluminum content increases, you see that the strength goes up, then you lose your ductility. But you look at the A10 aluminum 0, that is, which is having a huge elongation up to 65% it shows, and then you can vary this with alloying additions very nicely. It is similar to what we have looked at in hardness. Hardness and these curves will match, they are complementary. That is why it is written, compared to the hardness and compression test, tensile experiments are sensitive to detect embrittlement. Okay, we will be able to do that. Do you know why? Compared to the compression test, tensile experiments are sensitive to the defect embrittlement, to detect embrittlement. Yeah. So, in a tension, you always try to increase the stress concentration in any of the defect present. So, that will facilitate the fracture very fast. But in a compression, you always try to close the pore, void, defect. You are not producing any tensile stress at the interface of the defect and the matrix. For the high entropy alloy sample with the dendritic structure and some shrinkage pores, tensile tests are more suitable to reveal the mechanical properties in the stressed state, which is frequently encountered in the practical applications. So, what are the description of these stress strain curve? The shape of stress strain curves are highly affected by the structure of the high entropy alloys. And what we have seen is a typical tensile stress strain curve for aluminum, cobalt, chromium, iron, manganese, nickel, high entropy alloys. They are single phase FCC region represented by A10, 4, 17 and 18. Alloys behaved like a solid solution with a relatively low strength but exceeded ductility. But as the aluminum concentration increases, then it becomes FCC plus BCC phase represented by aluminum 9, 10 and 11. Alloys behaved like a composite with a sharp increase in the strength but reduced ductility. In the single phase BCC region, alloys becomes completely brittle. So, this is very important what we are looking at. We witnessed the highly brittle experience. So, we look at the other alloy systems, cobalt, chromium, iron, manganese, nickel alloy with the 6 testing temperatures with fine grained and coarse grained materials. So, this is quite interesting. So, you have a test done at a different temperature as well as the different grain sizes, very interesting combination. So, what you are looking at is the stress strain curves of cobalt, chromium, iron, manganese, nickel alloys with 3 different grain sizes, 4.4 micron, 50 micron and 155 micron. Fine grained materials have higher strength than the coarse grained material, which is well known. Small load drops after yielding were observed in the fine grained materials, while the stress strain curves of the coarse grained material show neither well defined yield points nor load drops after yielding. Okay. And also we have serration behavior occurs at 673 Kelvin for a fine grained material and as well as coarse grained material. So, this is well known. So, what is that we are learning from this slides? So, the strengthening mechanism, conventional, whatever you see in a conventional alloys as a strengthening mechanism is also applicable in the high entropy alloy systems, and that is clearly exhibited in the study. And what about the yield strength ductility combination? So, that is what you have to compare with the conventional alloy systems. So, the high entropy alloys display both yield strength and ductility at room temperature with a wide range. So, you can see that yield strength is going all the way beyond 1200 MPa, and then ductility also goes all the way up to 90. So, you have a range of properties are available to choose, where you can, all these aluminum alloys, super alloys, stainless steels, titanium alloys, they are all falling in these different domains. But the high entropy alloys opens up the major door to tune the strength and ductility combinations in this plot. The tensile yield stress of this aluminum, cobalt, chromium, copper, iron, nickel alloy and its variants of different cobalt are superior to Ti64 and inconel 713. And cobalt, chromium, iron, nickel has a better ductility than the conventional alloys such as 314 stainless steels and Ti64, inconel 713 and 5083 aluminum alloys. The temperature effect on the tensile properties studied in aluminum 0.5, cobalt, chromium, copper, iron, nickel and cobalt, chromium, iron, manganese, nickel systems. Okay. As shown in this figure, the yield stress decreases, the temperature increases for a single phase cobalt, chromium, iron, manganese, nickel, and the mechanisms of the temperatures on the yield stress are revealed. Yeah. So, the tensile yield stress as a function of temperature for three kinds of most studied high entropy alloys as shown here. So, this is an yield strength and this is as a function of temperature. You can see that you have three kinds of high entropy alloys. One is annealed, one is cold rolled and another is as cast. So, these three are as cast and forged, you can see that, and then with three different grain sizes also shown here. So, what is most interesting is the cold rolled high entropy alloy exhibit a very high yield strength, which is expected. As the temperature goes up, the drop of the strength is quite steep for the cold rolled, and of course you have a very fine grained material have very smooth transition of the strength. It loses strength smoothly as the temperature increases as compared to the other conditions. So, you have this, what we are seeing is these two alloys exhibit a strong temperature dependence decrease in strength with increasing temperature and relatively weak strain rate dependence. Okay, this is very important. So, the strain rate dependence, right, the material is sensitive to strain rate or not. This is also important because why this is important? Strain rate sensitivity. Why strain rate dependence of the material is important? Sure, strain rate sensitivity, yeah. So, it is basically resistance to necking. So, the deformation rate is controlling that, okay, especially at high temperatures. Mostly these are all discussed at high temperatures, but I am not very sure how you can explain this at room temperature, unless you have this adiabatic heating or something happens. No, those are all fine, but that is for the general idea that is still valid. For example, if you take titanium alloys, we are now observing negative strain rate sensitivity even at the room temperature test sometimes. So, those are all related to some of the defect structures develops and so on. There are some specific cases which need to be really looked at. We cannot be generalized. Okay. See, this aluminum, cobalt, chromium, copper, iron, nickel alloy was more ductile and strong after hot working than the as cast condition. The strengthening and toughening characteristics are mainly due to small grain size. Interestingly, the hot worked alloy showed a superplastic like behavior in the temperature range 1073 to 1273. And the tensile elongation was above 400% and reached 860% at 1273. These are all very extraordinary properties which you cannot imagine in the conventional materials. Okay. Having discussed about the tensile properties, we just quickly review the deformation mechanisms, which I have already shown yesterday in the characterization slides. What are the factors which are important in the light of high entropy alloys? TM is used to characterize the microstructure of most of the tension tested samples. So, what is shown or reported for the cobalt, chromium, iron, manganese alloy, that the initial plasticity up to the tensile strain of 2%, that is, you are observing a plasticity exclusively by a planar glide of 110 dislocation on 111 planes at room temperature. At higher strains with the room temperature and above, slip become more homogeneous and cell structures develops. Okay, so the moment you say cell structures develop, that means you are facilitating the defect motion in 3 dimension. Otherwise, cell structures will not form. Okay, the moment you see a cell structure, that means your deformation is homogeneous. It is not like a planar slip activity which restricts the defect motions everywhere. So, this dislocation motion is similar to normal FCC metals. However, at low temperature 77 Kelvin, extensive deformation twinning is observed. We have also seen yesterday, extensive deformation twinning is observed in the specimen deformed to a plastic strain of 20.2%, which is not common in a normal FCC metals. This deformation induced twinning by providing an additional deformation mode likely contributes to the observed increase in ductility at low temperatures. Yesterday also we talked about it. When you do a deformation at very low temperatures, you get an additional deformation mode. So, you have a slip and twinning, and this is that is a normal deformation. So, you have an additional deformation mode called nano twinning. We talked about nano twinning yesterday. So, such mechanisms are also possible in high entropy alloys, which makes them more attractive for the low temperature application, which is not possible in conventional idea. And the fracture surface also we have already looked at it, and this is for the as rolled aluminum 0.5 cobalt, chromium, copper, iron, nickel tensile tested sample at different temperatures. And what is that you are seeing here? This is room temperature 773, 873, 1073. What is that difference you are seeing? Now, what happens to this fracture morphology? This is a room temperature. This is slightly high temperature, 873, and this is what happens? More ductile. Yeah. From quasi-cleavage to more ductile mode it changes. You can see the elongation of this voids and everything happens. So, let us compare the fracture surface after compression and tension in 2 different ways, 2 different features, right. The fracture mode of this alloy transfers from the brittle to ductile types as the temperature increases, as we have seen in the previous figure. The fracture surface of this alloy undergo shear rupture at room temperature, ductile one at 873 and greater ductility at larger dimples at 1073. We have seen that elongated dimples also. At a certain temperature, high entropy alloys exhibit a mixed type of brittle and ductile fracture. For example, taking aluminum, cobalt, chromium, copper, iron, nickel, for example, the fracture morphology at 873 is a mixed mode of brittle to ductile fractures. Of course, the brittle fracture is reflected by presence of flat facets with the characteristic of river pattern markings inside the large dimples, while the ductile fracture is reflected in numerous dimples of different diameters surrounding the flat facets. So, what we are trying to understand is to try to compare this fracture surface under compressive and tensile loading. We predominantly see the consistent fracture mode, especially for these alloy systems. Yeah, so looking at this hardness, compression, tensile property relationship, so you can you can see that the yield strength versus temperature plot, and yield stress divided by hardness, that is normalized with hardness versus temperature plot, gives an idea for this two high entropy alloys. So, the transition of this yield strength after annealing is not drastic with compared to temperature as compared to the hot rolled or cold rolled conditions, and you can also relate that with the hardness changes, how this is changing with yeah, they are all very conventional ideas. So, you have both cold rolled and annealed samples. The ratio of tensile yielding stress versus hardness are lower than the constant 3.5 predicted by Tabor. Somebody has modeled it. No matter how high the temperature is, however, the constants are very similar in magnitude. Compressive yield stress is the stress state caused by the applied load that acts to reduce the length of the material along the axis of the applied load, while the tensile yielding stress is the stress state caused by the applied load that tends to elongate the material along the axis of the applied load. So, the compressive strength of high entropy alloys is generally higher than the tensile strength, which is also similar to conventional alloys. In this case, for example, the compressive and tensile yielding stresses at room temperature are 460 MPa and 360 MPa for aluminum, 0.5 cobalt, chromium, copper, iron, nickel respectively. Okay. So, this is generally because materials loaded in tension are susceptible to stress concentration such as material defects or abrupt changes in the geometry. That is why we do dog bone shape. So, they are very sensitive to tensile loading rather than the compression. The other important property we want to check is fatigue properties. Fatigue properties are important because most of the industrial and engineering applications requires this data, and then we look at this behavior for this alloy, aluminum, 0. cobalt, chromium, copper, iron, nickel, high entropy alloy. These fatigue properties are evaluated by 4-point bending test in this case. So, this is a basic idea about this, the maximum stress on the tensile surface with the span of two outer spins. This is a geometry by which you do the 4-point bending. It is a conventional testing, standard testing. So, the maximum stress is given by this formula. This is available in most of the strength of material books and all the textbooks. And where P is the applied load, S is the outer span length, and SI is the inner span length, B is the thickness, and W is the height. So, you get this sigma, and what we are interested is this data. Fatigue, you have a typical SN curve, that is stress range versus number of cycles to failure. What normally people characterize out of this plot is an endurance limit. So, you can see that the tests are conducted all the way up to 10 to the power 7 cycles, right. And then you have two kind of trends. You have a strong fatigue properties and another is a weak fatigue properties. That means it is the red dots coming down as a function of cycles, the strength range comes down. That means what? That means the material is try to soften very fast. That is why it is marked as a weak, and these blue dots are slowly coming down in the stress, and then they last for large number of cycles. And then beyond that, people characterize this as an endurance limit. This arrow indicates the corresponding endurance limit. So, these points are generally scattered within the range, stress range between 600 to 1200 MPa. Even at the largest stress range, 1100 MPa, the fatigue life is still scatters from 35,000 to 4,50,000 cycles. for this kind of scattering, the one possible reason could be the defects introduced during the casting and rolling process, such as aluminum oxide particles. That is what this EDS is shown here. Most of the aluminum oxide particles are there. So, any random kind of data, huge scatter in this fatigue properties will clearly show that your microstructure is not homogeneous. It has something is there, okay. Because the defects may serve as a nucleation site for micro cracks and shorten the fatigue life of high-entropy alloys. And you can see that in typical fracture surface, which is very different from the compression or retention. You see that micro cracks, and then you have a crack propagation region and final fracture region. This is a loading direction, and these are all the initiation site from the surface. And then you see nice fatigue striations here, which is not possible in a conventional compression or tension load, okay. And then you see the lot of dimples in the final fracture regions. So, you have a characteristic fracture surface after fatigue, which are observed in the high-entropy alloys also. Let us compare this because fatigue and all requires quite a bit of time and volume of materials to characterize all sort of materials. So, people have conducted very limited fatigue test, then they try to characterize the SN curves. So, we are now with that kind of data, we are trying to compare that with the conventional alloys. What we are seeing is in this plot, you have HEA domain, hatch region, all the data points are here, and the bulk metallic glass is marked in the green domain here, and all the traditional materials are here. So, you can see that high-entropy alloys, since they are having very high strength, they also have very high fatigue endurance limit, because endurance limit is directly proportional to the UTS of the sample. So, you have all the, so again the scatter is basically because of the casting defects, and this figure shows the endurance limit increases linearly with the ultimate tensile strength. So, this is a correlation between endurance limit and ultimate strength limit, and then they are compared with the conventional materials. And then you see that high-entropy alloys are placed at a very high UTS and endurance limit domain, okay. So, all these results indicate that high-entropy alloys are promising candidate materials in the structures requiring fatigue resistance for future applications. And one last thing which we want to talk about is indentation or nano indentation creep. This is also quite popular technique to evaluate the mechanical properties, where you have a very limited volume of material available with you. From there you can derive significant amount of information. So, indentation creep has been identified as a time dependent motion of a hard indenter into the solid under a constant load for a long time. That is an elongated hard test. So, anything we talk about the creep means a time dependent phenomenon, right. So, time dependent deformation. We will talk about creep behavior tomorrow when I show the high temperature behavior of this material. But we are talking about this as a room temperature or high temperature both. Typically, indentation creep experiments were done for aluminum, cobalt, chromium, iron, nickel alloys as with the increasing in aluminum content. I think this particular material, if you in the literature you have all sort of data is available. It's quite popular with increasing in aluminum content in the range of 773 to 1173, using 1 kilogram force for load for a dwell time of 5, 10 and 30 seconds. And this creep behavior is strongly dependent on the crystal structure of high-entropy alloys. And this particular alloy is an FCC having a FCC crystal structure, a single phase. and hot hardness resist without large change for all the experimental temperature in the time range of 30 seconds. So, no obvious creep occurs in a single phase FCC at high entropy alloys even at high temperatures, which suggests that the main deformation mechanism is slip. Okay, so creep is also a deformation mechanism. The variations of the hot hardness as a function of dwell time are negligible. You see, this is what we are seeing. It's negligible, no? You are not seeing any difference. But the increasing dwell time, there is some response. Okay. So it confirms that the creep happens for the multi-phase high entropy alloys above certain temperature. So not a single phase, but in effect. So that is another information. If you follow, when the aluminum concentration is very low, as the aluminum concentration increases, it becomes FCC. It is BCC. So obviously it will have a. So this is way of looking at this data, like nano indentation is the initial transient creep stage of any alloy, but in this case what we are showing is by this Wang et al. What they have known. It's viscoelastic fitting theory, high entropy alloy, and empirical describe the displacement curve for the initial creep stage as a function of time, Hi plus beta plus Kt. Beta m k are fitting, and fitting protocol for this equation is found for this alloy at a constant Newton as shown in this figure. Conventional alloys, the crossover point where the slope creep stage is found in the iron alloy. What is that you are seeing? Here it is Ht, so height as a function of time, crossover point. What is the significance of this crossover point? Material dependent, and also the you are measuring the depth as a function of time. How yeah, you minimize it, and also it is a, but you fit the data with constants, right? So we have a linear relationship. So is there any different capture the material property parameters? That's the idea. Of course, they will use error fitting and everything they will use details for this idea, but generally when you say they do, because they are capturing material response by plotting this, and the crossover means you have changing to one to other deformation mechanism. Okay. So that's what is shown here. So you can see that time dependent yielding point and the holding load dependent plot. So these kind of studies, indentation studies, shows that the value increases with increasing holding time at the with increasing the loading stress at constant. You see that there is a clear relationship between and the A hypothesis proposed for the crossover point is that initially, from a viewpoint of dislocation indenter, the formation of behavior. So you see that now we are coming with what is actually happening in the material. So you have dislocation migration and then cell formation. Okay. Before the crossover point, the separated dislocation and entanglement leads to the work hardening effect. So now we will go back and then see. So it is going like this, and then here it is different slope. So you have a dislocation, migration, pile up, everything. Then the cell structure forms, then it behaves very differently. After the crossover point, the work hardening effect is saturated and the residual dislocations migrate into domain boundary of the dislocation cell, which determines the viscous behavior. So, this is a hypothesis. Okay. This is one hypothesis. It is not that it can be shown in every material. People have looked at the indentation creep, and then they try to understand how to get the idea about deformation as a function of time. So, that is one idea. With that, I will stop and I will continue this tomorrow with high temperature deformation, and with that